Okay, let's talk about the high-low network and how to solve it algebraically. And it's basically just an application of circuit theory, right? So there is some equivalent impedance here, Z sub n, looking down this network. Okay, so here is the load, and here are just some purely reactive elements. And I would like to choose these values, x and b, to create no reflections into this network. So, all right, so let's just write this out. Z sub L is equal to R sub L plus J X sub L. And I have some input impedance here. So you notice if I'm looking in, it's the series combination of this term plus the parallel, or it is this term here in series with this parallel combination, right? So I'm going to write it out as Z sub n is equal to Jx in, plus, because it's in series, and then the parallel combination of that. So I'm going to write JB in parallel with Z sub L. Okay, so let's just write that out algebraically. Z sub n is equal to Jx plus, and we're going to write it like so, 1 over J, well, so remember, this is an admittance here, right? So the 1 over is already happening. So I'm going to write JB like so. So again, admittance, if this were an impedance, I'd have to do a 1 over, but since it's already an admittance, I'm just going to add it with plus 1 over Z sub L, like so, and then that's a 1 over there. So that's the parallel combination of these two terms. And put in this little term here. So we're gonna, and we also want this to match to be Z naught. So that's all we're gonna do here. So we basically say Z naught is equal to Jx plus, and let's just write this out maybe a little more neatly. Something like this, 1 over JB plus 1 over R sub L plus JXL, like that. Okay, so you notice it's just algebra, but it's going to get a little bit hectic. But the idea to bear in mind is these two things, I can set them to whatever the heck I want such that they cause a match with these two. So these two terms are fixed and given, but these can be specified however the heck I like. And what follows now is a giant mess of algebra, right? Like, for example, first things first, I'm going to cross multiply. So I might get something like Z naught times JB plus 1 over R sub L plus JXL equals JX times, again, JB plus 1 over R sub L plus JXL plus 1. Okay, and the derivation just kind of keeps going. You mix and match a bunch of terms. We don't necessarily have to go through every step. It is kind of painful to do it. I did the first one, and it took me a few minutes. But what you have is essentially a bunch of real values and imaginary numbers. So you equate the real values to each other and equate all of the imaginaries. And it can be shown. You just do some algebra here. Just write this out, algebra. So the details aren't super important. You can do this. I did do it and it was painful, but you eventually arrive at two simple equations. B times Z naught R sub L minus X sub L is equal to X times 1 minus BX sub L. So I think that's what happens when you equate the real parts to each other. And then when you equate the imaginary, you get B times X RL minus XL, times Z naught, pack that in there, is equal to R sub L minus Z naught. So this is in the book. They kind of skip all these steps, but you can eventually get to here. And this is two equations with two unknowns. Two equations, two unknowns. So obviously there has to be some unique solution here. And you do yet more algebra still. You solve for, say, B in terms of these other terms, and you mix and you match, and something special will happen. So you eventually find that B is equal to the following. And I'm going to get an X sub L plus or minus, you get a quadratic equation basically, square root of R sub L over Z naught times, and this is going to be a little yucky, R sub L squared plus X sub L squared minus Z naught R sub L, square root that, and then I get an r sub l squared plus x sub l squared. So it's a pretty yucky quadratic expression here, but you can put this into MATLAB, and you notice there's no x term here. These are all known parameters. And then when I solve for b, you can finally calculate your x using the following: 1 over b plus x sub l z naught over r sub l minus z naught over b r sub l. So this is the, so you can see how pretty painful that gets, right? They're very nasty algebraic expressions. And in the advent before nice handy computational tools like MATLAB, this would be a bit painful to work on a calculator. And so you can see the appeal of trying to visualize this using the Smith charts. But they are nice closed form expressions that you can just plug it into MATLAB and get simple results here. You also notice there are two results, the plus or minus, corresponding to those two possible solutions here in terms of intersecting with the circles. Okay, so now that we're all settled on the high-low solution, let's go ahead and take a look at the low-high, which I've already drawn here. And again, the argument is the same. You just calculate the equivalent input impedance here, and I want it to equal z naught. So you notice it'll be this in series with that, and then in parallel with that. And again, it's a really nasty derivation, but it's just algebra, and it can be done. But we don't have to waste our time on that because it's just big and it's ugly, and the results have already been done, or tabulated, I guess. So what you find is x is equal to plus or minus, you get r sub l z naught minus r sub l square root minus x sub l. And then you find b is equal to plus or minus, and you get this kind of thing. So I get a z naught minus r sub l over r sub l square root that z naught. So this is in the book if my handwriting isn't the cleanest. But those are the solutions there. So again, this can just be dumped into MATLAB to get very straightforward solutions. And because of the plus or minus, there are two options here. And I think the way it works is for the minus has to correspond with a minus and plus corresponds to plus. But we'll double check that in the textbook. So for MATLAB, that's obviously no big deal. And yet again, just to kind of emphasize, you can see this appeal in thinking about it more in terms of a visualization in the Smith chart, that you're just following these circles from a couple of paths to get to the origin. So that is one of the major reasons why Smith charts are generally very popular, is you can think about this in terms of these horrible, nasty algebraic expressions, or you have this nice analog computation that you can just follow in the Smith chart here. So we'll try and do a few problems where we look at the Smith chart and track these values so you can see what's happening. And then we'll also write some MATLAB codes that grind on these expressions as well. And then what we'll also want to do is, once we have these parameters here, it's very helpful to do a frequency response, right? So you'll have something that maybe looks like this, where there'll be a center frequency, f sub 0. So this is frequency. And then you want to plot the magnitude of gamma, and maybe on a linear or logarithmic scale. And what you'll usually see, is something where it goes all the way down to 0, and then it kind of pops back up again. And there'll be some nice bandwidth associated with these matching networks. So that's kind of the advantage of these. Now, something to be mindful of is lumped elements aren't the best thing for super high frequency, right? Because if I have a capacitor, it isn't really just a capacitor. A far better way to think of a capacitor is something like this, right? So there's a tiny bit of inductance and resistance in parallel with any given capacitor. There'll be some dissipation there. And so as you get very, very high in frequency, these little parasitic parameters start to really add up and cause trouble. So the book kind of suggests that, as a general rule, lumped element matching is nice, but you probably want to keep it under a gigahertz or so. Okay, as you get above a gigahertz, this method isn't ideal. just mostly because a capacitor or an inductor, a capacitor is no longer really a capacitor, and inductors are no longer really inductors, right? And especially as you get very high in frequency, you'll be dealing with like femtofarads and pico henries and that sort of thing. It gets very difficult to precisely manufacture this stuff. And then just the parasitics of your wiring itself can cause trouble as well. So that's a nice little rule of thumb for when this particular method is practical, right? Because little ceramic chips parts are very precise, but only up to a point. Okay, so there you go. So we have the MATLAB code that we can write that will just grind on these expressions for us and give us our solutions. And then we also have the graphical visualization of what's going to happen as we play around with these parameters, right? So what we'll do is some homework where I might give you some load, and you're going to start here, and you're going to just add some series inductance and watch, plot the curve as it follows these circles here. And then you'll add the parallel admittance, and you'll see it suddenly take this right turn and follow the other circle as well. All right, so there you go. So that's lumped element matching in a nutshell.